Hello everyone and welcome to this video for the Level 3 2022 Aqueous paper for Level 3 Chemistry. So we're going to get straight into it at question 1, looking at A. So we're going to write the equation for the equilibrium occurring in a saturated solution of silver chromate, which is Ag2CrO4. So for this equation, we know that the silver chromate is going to partially dissociate in water to form its ions. So we're going to have Ag2CrO4 in the solid state. And it's going to partially dissociate to form its ions, which is going to be 2Ag plus in aqueous state plus CrO4 minus ions in aqueous state. Yeah, and that's it for part I. And now we want to write the expression for the solubility, so Ks of silver chromate. So in this case, Ks is equal to we have a coefficient of 2 in front of the Ag plus, so that's going to be Ag plus to the power of 2, the concentration of Ag plus ions squared, multiplied by the concentration of CrO4 minus. And since Ag2CrO4 is in the solid state, we won't consider that in our expression for the Ks. So our expression for the Ks is simply Ag plus squared, the concentration of Ag plus squared, multiplied by the concentration of CrO4 minus. Part II, we want to calculate the solubility product Ks of Ag2CrO4 in water at 25 degrees, given that the solubility is 6.5 times 10 to the power of negative 5 mole per liter. So in this case, we have some solid, and it's going to dissociate to form 2 lots of Ag plus ions and 1 lot of CrO4 minus ions. And we're going to let the solubility be S. So we're going to say let solubility be S. So some S amount of Ag2CrO4 is going to dissociate to form our ions. So therefore, we're going to have 2 lots of S is going to be our Ag plus ions. And we have 1 lot of S is going to be equal to CrO4 minus. So therefore, we can plug this into our expression for our Ks. So we can say Ks is equal to 2s to the power of 2 multiplied by s, which is 4s to the power of 3. And therefore, 4 times off the solubility, which is given as 6.5 times 10 to the negative 5. So we have 6.5 times 10 to the power of negative 5 to the power of 3 should give us our answer, which is going to be equal to 1.1 times 10 to the power of negative 12. So that will be our answer for the solubility product Ks at 25 degrees. And this will be a merit level question, okay, for part for part 1, 2, and 3. So this is a merit level question if you can get up to this step here. And to get an achieved, you can have a correct equilibrium expression, so correct equilibrium expression and correct method for Ks. So I think these two here will be enough to get you the achieved right there. Question B, we're going to explain using equilibrium principles the effect of the following on the solubility of Ag2CrO4 in water. You want to include relevant equations in your answer. So what happens if dilute silver nitrate is added? So if dilute silver nitrate is added, we know that silver nitrate is going to give us Ag plus ions, and it's going to give us NO3 minus ions. And if we increase the concentration of Ag plus ions, the equilibrium will shift to reduce the change. So in this case, the concentration of Ag plus increases, so the equilibrium will shift to favor the reactants. So it will shift backwards to favor the reactants. Therefore, less of the solid, Ag2CrO4 will dissociate to form its ions in water. So therefore, the solubility will be decreased. So I just want to link those points together. So when we add AgNO3, I'm just going to put the bullet points on the points you should be mentioning. So we want to mention that Ag plus ion concentration increases due to the AgNO3. So if the Ag plus ions increases due to the AgNO3, the equilibrium will shift to reduce the change. So equilibrium will shift to reduce the change. So in this case, Ag plus is a common ion, so we can say Ag plus is common ion. So equilibrium shifts to favor the reactants. Shifts to favor the reactants. Therefore, we can say less Ag2CrO4 will dissolve in water. Dissolves, so therefore solubility will decrease. Alright, so that's part BI, and we can look at part II. So what happens if dilute sodium cyanide, NaCN, is added? So in this case, NaCN is going to give us Na plus ions and Cn minus ions in aqueous state. So we have NaCN. That's going to give us some Na plus ions. And that's going to give us some Cn minus ions. And if you notice on the formula sheets they give you for level 3 chemistry, you will notice that there's existence of a complex ion which is called AgCN2 minus. So this is a complex ion that will form in the presence of Ag plus and Cn minus ions. So in this case, we're going to have a reaction of Ag plus added to 2 lots of Cn minus ions. This is in aqueous state. And that's going to give us the complex ion. So complex ion AgCN2 minus. So what does this do? Okay, so in this case, we're seeing that some Ag plus ions are reacting with the excess Cn minus ions produced by the NaCN. So therefore, Ag plus ions is being removed from the equilibrium to form this complex ion. So therefore, again, there's going to be a shift into equilibrium to reduce the change. In this case, the amount of Ag plus ions is being reduced. So it's going to shift to produce more Ag plus ions. So more Ag2CrO4 will be able to dissolve. So therefore, the solubility will increase. So in this case, it's the exact opposite of what we had before. So in this case, we have Ag plus ions. Concentration is decreasing. Decreases as Ag plus and Cn minus form complex ion. Forms a complex ion AgCN2. Therefore, equilibrium will shift to reduce the change. So more Ag2 CrO4 will dissolve to form more Ag plus ions to replace some of those that have been reacted. So we say more so it produces more Ag plus and CrO4 minus ions. So the forward reaction is favored. So forward reaction favored. And finally, we can say solubility increases. Yeah, that's really all we need for this question. So just linking those few bullet points together. That will be a excellence level grade if you can get both part I and part II is correctly justified is an excellence. To get a merit, if you can explain either one of them, that's a merit. So either I or II is a merit. And to get an achieved, if you can recognize that Ag plus increases or decreases in either of those situations, that will be an achieved. Cool. Let's look at question C. We want to show by calculation that a precipitate of silver chloride, AgCl, it will be forming when 30 milliliters of 0.0686 mole per liter calcium chloride, CaCl2, is added to 50 milliliters of 0.00154 mole per liter silver nitrate and AgNO3. So for these questions, I always like to write out the equation for the dissociation of the solid in water. So we have AgCl, and it's going to dissociate to form Ag plus ions and Cl minus ions. And therefore, the expression for the expression for Ks will just be equal to concentration of Ag plus multiplied by the concentration of Cl minus. So that will be the expression for the Ks constant for this equilibrium. And now for this question, we want to relate the number of amount. So amount of ions. I want to link that to the total volume and therefore the concentration of ions. And then we want to calculate the ionic product. We'll call it Kp. We want to find the ionic product. And then compare this to the Ks value. Compare to Ks value. Okay, so let's just calculate the amount of CaCl2 in the reaction. So we have N of CaCl2 that is equal to C times of V. So that's going to be 0.0686 multiplied by 0.03, which is going to give us, get a calculator. Give me a moment to get a calculator out here. Calculate. Sorry, just give me a moment. It's being a little bit frustrating at the moment. Okay. Okay, so we have 0.0686 times of 0.03. That's going to give us 0.002058 mole. And we want to find the concentration of Cl minus ions. So we know that CaCl2, so CaCl2 aqueous, will give us one lot of Ca2 plus ions and two lots of Cl minus ions. So the stoichiochemical ratio here is 1 to 2. So the actual amount of Cl minus ions is equal to 2 times of 0.002058. Which is 0.04116 moles. And we want to find the amount of Ag plus ions. So the amount of AgNO3 is equal to 0.05 multiplied by 0.00154. So that's 0.05 times of 0.0154. And that's going to be equal to 0.00077 mole. And we know that AgNO3 is a 1-to-1 stoichiochemical ratio, so we don't need to multiply by any constants here. So we have 0.00077 moles of Ag plus ions. So now we can convert this to the concentration by dividing by the new volume of the solution, which is a total volume 80 milliliters. So now the concentration of Ag plus is 0.00077 divided by 0.08. That is approximately 0.009625 mole per liter. And the concentration of Cl minus is equal to 0.002058 divided by 0.08. So it will be 0.002058 divided by 0.08. That is equal to 0.025725 mole per liter. And now we want to find the ionic product. So the multiplicative product of Ag plus and Cl minus will give us the ionic product, as we see from the Ks expression. So that's going to be the product of these two values we just calculated. That's going to give us a value of 2.48 times of 10 to the 10 to the negative 4. Okay, so this is actually much greater than the value of Ks. So this is much greater than Ks value. So therefore we expect this is much greater. So therefore we expect. Okay, sorry. So since the ionic product is much bigger than the Ks, therefore we expect the equilibrium to shift to the left. So therefore there will be a precipitate of AgCl forming. Since the ionic product is greater, the equilibrium shifts to the left to favor the reactants in order to bring the product back down to the Ks value, to the equilibrium value of 1.8 times 10 to the power negative 10. If it shifts to the left, then we expect some precipitate of AgCl to form. I'm not going to write it here since I've run out of space, but that's what you would expect to be saying for that question. So just saying that IP is greater than Ks, so therefore we would expect some solid of AgCl to be forming there. Okay. Okay, I think. Okay, I think I've made a little bit of mistake here. My answer does not line up with that of the answer schedule, so I must have done something not quite correct here. So let me just really quickly check over my answers. So 0.0686 multiplied by per liter. Okay, let me just give me a moment. Apologies for the wait, but I think I've made a mistake here. So we have 0.08686 times 0.03. Yep. Oh, so I've used the wrong values. Okay, of course. Okay, my apologies. We've calculated the amount of Cl minus ions as 0.004116. Not this value. It would be 0.004116. So that would be 0.004116 divided by 0.08. So this is actually 0.05, so we have 0.055154 mole per liter, and hopefully this will give us the IP value is something different here. Okay, yeah, okay. That seems to be 4 point. Yeah, okay. So this would be not correct. So this would actually be 4.95 times 1, 2, 3, 4, 5, 0.00077. 0.05 times 10 to the power of negative 5. Yeah, that's the correct answer. Okay, so it's the same conclusion there. So same conclusion because IP is still greater than Ks, so we expect the solid of AgCl to be forming. So in terms of that is the same answer. Okay, so sorry about that. Apologies about that delay. If we can get back into question number 2. Okay. So we have sodium hypochlorite, NaOCl is an active ingredient in bleach. The hypochlorite ion OCl minus is a weak base. So we want to list all the species present in a solution of NaOCl in decreasing concentration, and we do not want to include water. So in this case, first thing that's going to be happening here is we're going to have NaOCl going to dissociate completely in water to form its ions. So we have NaOCl. It's going to completely dissociate to form some Na plus ions and some concentration of OCl minus ions. And then additionally, some of the OCl minus ions will react with water. So we will react with water in order to form HOCl plus OH minus ions. Okay, so and since OCl minus is a weak base, we know that only a very small amount of OCl minus ions will actually dissociate in water to form the HOCl and OH minus ions. So therefore, there's a small amount of HOCl produced and there's a small amount of OH minus produced. So in fact, the species that has the greatest concentration in this case is the Na plus ions. And this is because an equal amount of Na plus ions and OCl minus ions are initially produced. However, some amount of those OCl minus ions will continue to react with water. So we're going to lose some of the OCl minus ions by reaction of water. So therefore, there's going to be slightly more Na plus ions than OCl minus ions. However, there's still going to be more OCl minus ions as HOCl and OH minus. And this is because, the reason for that is because only a very small amount of OCl minus will dissociate in water since it is a weak base. So we see that OCl minus is still much greater than HOCl. And since we know that the concentration of OH minus multiplied by the concentration of hydronium ions, H3O plus, is equal to the constant, is equal to some constant at 25 degrees Celsius, which is 1 times 10 to the power of negative 14. We know that the hydronium ion concentration must be lower than that of the OH minus ion concentration and the HOCl concentration. So to start off with, we know that Na plus is the greatest, followed by OCl minus. And there's going to be some HOCl formed, so some HOCl, and that's going to be equal to the amount of OH minus ions formed, since they're formed in a 1:1 ratio. So it's roughly equal. It's not exactly equal, since water itself has some OH minus ions at the start. So H2O has a concentration of 1 to the power of negative 7 mole per liter of OH minus ions. So the OH minus ions is actually going to be slightly greater than that of the HOCl. However, it is a very, very small difference. So we can just say it's roughly equal to that of the OH minus ions. And the OH minus ion concentration is of course going to be higher than that of the hydronium, since we know that Kw, so the constant of 1 times 10 to the power of negative 4 at 25 degrees Celsius, is equal to the product of HO3 plus and OH minus. Alright, so that's our order for that question. Looking at question II. Hypochlorous acid, HOCl, is the conjugate acid of the hypochlorite ion. If a hypochlorous acid solution has a pH of 4.8, calculate its concentration. So we're going to write the equation for the reaction of HOCl with water. So we have HOCl reacts with water, and that's going to be forming some concentration of OCl minus ions and hydronium ions. And therefore the expression for Ka would be equal to the product of hydronium ions multiplied by the concentration of OCl minus ions divided by the concentration of HOCl. So in this case, we know that our Ka value and we know the pH value. So we know, if we know the pH value, then we know the hydronium ion concentration. So we know that the concentration of hydronium is equal to 10 to the power of negative pH, which is equal to 10 to the power of negative 4.8. And for this question, we will assume that the OCl minus ion concentration and the hydronium ion concentrations are the same, since they're produced in a 1:1 ratio. And in reality, like I said in part I, the hydronium concentration is actually slightly bigger than that of the OCl minus concentration, since initially in water there is a presence of hydronium ions. However, we will assume that this concentration is negligible compared to the amount of hydronium ions produced by the reaction of hypochlorite acid with water. So therefore that's negligible, so they're equal. So we're going to assume that they're equal. And we will assume that the final concentration of HOCl is equal to that of the initial concentration of HOCl. Since HOCl is a very weak acid, only a very small amount of HOCl will dissociate in water to form its ions. So we will assume that this amount is very small to be negligible, so that the initial concentration of HOCl is equal to that of the final concentration of HOCl. So we're just going to plug in the initial concentration of HOCl as our assumption is no change. So if we plug those numbers in, we can find the HOCl concentration. We have Ka equal to 2.95 times 10 to the power of negative 8. That is going to be equal to 10 to the power of negative 4.8 whole squared divided by the concentration of HOCl. And if we rearrange to find HOCl, so HOCl is going to be equal to 10 to the power of negative 4.8 squared divided by 2.95 times 10 to the power of negative 8. And this will be equal to a concentration of 0.00851 mole per liter. And that's our final answer. So we look at part III. So we want to compare the electrical conductivity of HOCl and NaOCl solutions of equal concentration. We want to use relevant equations in our answer. So in this case, if we want to look at NaOCl NaOCl, that is a basic salt and we call it a basic salt because NaOCl will dissolve completely in water to form Na plus ions as well as OCl minus ions. However, OCl minus ions will continue to react with water by taking one of the hydrogens from water to form HOCl. So it will form HOCl as well as some OH minus ions, and the excess OH minus ions causes the solution to become basic, so therefore we call NaOCl a basic salt. So for NaOCl as a basic salt, it will dissociate completely in water, completely to form Na plus OCl minus ions. So that will be producing NaOCl. It's going to be producing Na plus OCl minus ions. And if you want to write out the equation for OCl minus, you can. So it will just be OCl minus. It's going to react with some water, and that's going to be producing some HOCl as well as some OH minus ions. However, in terms of the concentration of ions, which we really care about, the concentration of ions is really high. So we can say that the concentration of ions is high. And this is because NaOCl completely dissociates to form its ions. Therefore, the NaOCl it will be a good electrical conductor. So alright, so let's look at HOCl. So HOCl is different because it is a weak acid, and a weak acid will react partially with water to form OCl minus ions and excess hydronium ions. So we have HOCl reacting with water, and that's going to be forming a small amount of OCl minus ions and a small amount of excess hydroxide ions. So we can say that HOCl is a weak acid. So it partially dissociates to form its ions. So it'll form, it's not OH minus, it's hydronium. I just realized I've made a mistake there, sorry. So it's hydronium ions there. Yeah, it's a weak acid. Yeah, my apologies. So we have hydronium ions there. So form some ions of hydronium and OCl minus. However, this is a very small amount. Therefore, the concentration of ions is low. Concentration of ions is low, hence HOCl is a poor electrical conductor. And that's it for that question. So now we'll look at a question. In terms of the marking for that question, it's definitely going to be an excellence level question. If you can fully compare the electrical conductivity of both solutions and include relevant equations, that will be an excellence level grade. So if you can get correct comparison of HOCl and NaOCl, you'll get an excellence. If you can correctly calculate the original concentration of HOCl, that's a merit. So this is a merit level question. To get an achieved, if you can order the species correctly, 3 ordered species correctly is an achieved. Okay, so let's look at question B. When a small volume of hydrochloric acid is added to a buffer solution made from HOCl and NaOCl, the following reaction occurs. So OCl minus is going to react with some hydronium ions to form HOCl and H2O. So explain the significance of this reaction in terms of the buffer solution. So in this case, we have the basic part of the buffer. So the basic component of the buffer is OCl minus ions, and that reacts with the excess hydronium ions to form HOCl and H2O. So in this case, this is significant because once we add the excess hydronium, it actually reacts away with the OCl minus ions in the solution. So therefore, the pH of the solution will not reduce drastically. And this is because the excess hydronium ions is indeed removed by the OCl minus ions to form HOCl and H2O. So therefore, the pH of the solution does not significantly decrease in this change. In this case, it will decrease slightly, but it will not decrease as drastically as if there was no OCl minus ions in the solution. So we say that when excess is added, will react with OCl minus. So this neutralizes removes H, and hence there is no sudden decrease. There's no drastic decrease in the pH of the solution. So there's no drastic decrease in the pH of the solution. So there is still a decrease because more HOCl is produced. So there is still a decrease. There is still a decrease since more HOCl is produced. However, HOCl is a weak acid. So as we said before, HOCl is a weak acid. So not much of the HOCl will react with water to form hydronium. Therefore, the actual increase in hydronium is not very significant. So, however, HOCl is a weak acid. So, the decrease in pH is not significant. Maybe not significant. Maybe say it's not as large as pH not as much as if there was no OCl minus. Alright, and that is a merit level question, if you can get a correct explanation here. Alright, so let's look at question C. So question C, the pH of three solutions of equal concentration were ranked in order of increasing pH. We want to justify the order. So this is relative concentration of hydronium ions and relevant equations. It's pretty straightforward, this question, since we know HF is a strong acid. CH3COOH is a weak acid. And CH3COONA is a basic salt. So we have strong acid is a low pH, weak acid is a higher pH, and a basic salt is an even higher pH. So let's start off at HF. So HF is a strong acid, meaning it fully dissociates in water to form its ions. Which are H So we're going to form some hydronium ions as well as F minus ions. So it's a strong, so fully dissociates. So therefore, so a large amount of hydronium is Okay, so therefore, it's a large amount of hydronium is produced, and that's going to decrease. A larger amount of H is going to decrease the pH. And in terms of CH3COOH, that's going to be a weak acid. So CHCOOH is a weak. So CH3COOH is a weak acid. So in this case, it's going to partially dissociate to form its ions. So which are CH3COO minus and hydronium. Since only a partially dissociate, so since only a very small amount, since only a very small amount of CH3COOH dissociates, therefore a smaller amount of hydronium is produced. Hence the pH is higher than that of HF. For the last one, as basic salt, we have CH3COONA. That's going to be producing the, don't use that arrow, that's going to produce CH3COO minus and Na plus ions. And CH3COOH, COO minus in this case, is going to react with water. That's going to be producing CH3COOH and OH minus. So in this case, so we have the CH3COO minus is a weak base and will partially dissociate to form some OH minus ions and CH3COOH. So partially dissociates to form OH minus ions. So there is an excess of OH minus ions, so the solution is basic. So this solution is basic and therefore has the highest pH. Okay, so in this case, okay, so the answer schedule is saying that HF is still like a weak acid, but in terms of HF, is a little bit of a borderline since HF is definitely much stronger than CH3COOH. So I think, yeah, my classification of a strong is probably not the most accurate. So it's probably strong acid mostly refers to something that can fully dissociate in water. Yeah, but it's true that HF probably doesn't fully dissociate in water. So my classification here is probably still not extremely accurate. So I will. This is still partially dissociates, but it's definitely stronger than. Definitely HF is much stronger than CH3COOH. So it partially dissociates to form its ions. So you can say a larger amount of HO3 is produced, which decreases the pH. Since HF is stronger acid than CH3COOH. Yeah, so just be careful on the wording. Yeah, this is probably not the best wording on my part, since again, yeah, like a strong acid refers to full dissociation, so all of that acid will dissociate in water, while weak acid means that not all of that acid will dissociate in water. So the correct terminology will probably be saying that HF is a weak acid, but it is indeed I'm pretty sure it's orders of magnitude stronger than CH3COOH. So therefore, we do expect the HF to still have a lower pH than that of CH3COOH. Okay, so we look at question 3. Titration was carried out by adding 0.155 mole per liter nitric acid to 25 milliliters of 0.124 mole per liter ammonium. The equation is given below, so I'm not going to read it out loud, but we can see the equation. And we have a curve. So we want to calculate the pH of the 0.124 mole per liter ammonia solution before any nitric acid is added. So in this case, we're going to write out the expression for the Kb. So we have Kb is going to be equal to the concentration of NH4 plus multiplied by the concentration of NO3 minus divided by the concentration of NH3. And we know that, in this case, the Ka multiplied by Kb equals to 1 times 10 to the power of negative 14. Or in terms of pKa, so we have pKa plus pKb equals to 14. So therefore, Kb is equal to 1 times 10 to the power of negative 14 divided by the value of Ka, which is 10 to the power of negative 9.24. So that's going to give us the value of Ka. Okay, so Ka is going to be equal to, Kb is going to be equal to, I'm going to evaluate just that expression there. So if we grab a calculator, what am I doing? Okay, so we need a calculator, so give me a moment. Okay, so we have 10 to the power of 10 to the power of negative 9. 1 times 10 to the power of negative 14 divided by. Okay, so we have a value of 0.0000174. Okay, and now that's going to be equal to our right hand side. So we have Kb is equal to concentration of NH4 plus multiplied by the concentration of not NO3 minus in this case, because in this case we have NH3. NH3. So that's actually OH minus. Sorry, I'm being a bit sloppy today. So we have OH minus here, not NO3 minus, OH minus and NH4 plus, as we can see from our equation here. So Kb is equal to some OH minus squared, since we're going to assume that the NH4 plus concentration is equal to that of OH minus, and divided by the initial concentration of NH3, since we're assuming that there is no change in NH3 concentration. Okay, so we're going to multiply both sides by 0.124. Find the square root. So that's equal to, so OH minus concentration is equal to 0.00147 mole per liter. So therefore POH is the negative log of that, so negative. So that's going to be equal to 2.83. So therefore the answer would be 14. So pH is 14 minus 2.8, which is about 11.2. So 11.2 here will be the answer for our question. So 11.2, that's our pH. And this is a merit level question for the correct calculation. And let's move on to question B. So as HNO3 is added to NH3, the NH3 reacts to form ammonium ions NH4+. After a certain volume of HNO3 has been added, NH3 and NH4+ are present in the 5:2 ratio in the solution. So we want to calculate the pH of the solution and evaluate the effectiveness as a buffer. Alright, so in this case, we can just use our Ka expression. So if we have NH4+ added to water, it's going to give us NH3 plus hydronium. So Ka is equal to the concentration of NH3 multiplied by hydronium divided by NH4+. Okay, and we know that NH3 and NH4 are present in the 5:2 ratio. So therefore, we know that NH3 divided by NH4 is 5/2. So therefore, Ka equals to 5 times of hydronium over 2. So therefore, Ka we know from our previously here is 5.75 times 10 to the power negative 10. So 5.75 times 10 to the power negative 10 equals to 5/2 times hydronium. So therefore, the hydronium ion concentration is equal to 2.3 times 10 to the power negative 10 mole per liter. And therefore, our pH is negative log of hydronium. So that's negative log of 2.3 times 10 to the power negative 10, which is equal to 9.64. And in this case, since the pH is 9.64 and the pKa value is 9.24, so in this case pH is greater than pKa, so therefore the concentration of the basic part of the buffer is greater than that of the acid. So therefore the buffer is more effective at neutralizing added acid rather than base. And it's more effective at neutralizing acid because there's more base available to react with that acid when it's added, rather than if base is added, then there's less acid to react with the base. So therefore the buffer is more effective at neutralizing volumes of strong acid. So we can say that 9.64 is greater than pKa. So therefore higher concentration of base which is NH3. So the buffer is more effective at neutralizing added acid. Yeah, that's all we need for this question. And you can always do a sanity check because we know that the ratio of NH3 to NH4+ was 5:2. So 5:2 is NH3 to NH4+. So there's much more NH3 than NH4+. So there's more base than acid. So we arrive at the same conclusion as we did in our answer. Okay, perfect. Let's look at question II. So we want to explain the significance of the pH of the solution in the flask halfway to the equivalence point of the titration. So for this question, once we're halfway to the equivalence point of the titration, we know that exactly half of the NH3 has reacted to form NH4+. So there's exactly half of the NH3 left, producing exactly equal amount of NH4+. So that's an equal amount of NH3 and NH4+ in the solution, and it's going to be acting as a buffer. So at this point, the solution is acting as a buffer since there's going to be equal amounts of NH3 and NH4+. And at this point, the pKa of NH4+ is equal to the concentration, the pKa is equal to the pH of the solution. And that's about it. So that's all we really need to say here. So at equivalence point, I'm just going to abbreviate. So at equivalence point, half of the NH3 has reacted with added acid, so with added to form NH4+. So half of the NH3 has reacted to form with added hydronium to form NH4+. So there's equal amounts of NH4 plus and NH3. So there's equal amounts of NH4 plus and NH3. Therefore, the pKa is equal to pH. At halfway to equivalence point. So therefore, pKa equals to pH. And this point, pKa equals to pH, and the solution is acting as a buffer. So there's no significant change in the pH for small amounts of added acid or base. Alright, that's all we need for this question, okay? And this is an excellence level question for the correct pH and correct explanation. That's an excellence for both of these parts here. Okay, question C. In the second titration, 25 milliliters of 0.124 mole per liter sodium ethanoate is titrated with 0.155 mole per liter HNO3. The equation is given below, and we have the Ka value and Ka values of both of the species of NH4 plus and CH3COH. Predict how the initial pH will compare to the titration of NH3 by circling one answer. So initially, we have some CH3 COO minus, and that's basic. So this is a base. This is a base which is going to partially dissociate in water to form CH3COOH as well as hydroxide ions. However, in this case, we know that if the conjugate acid is stronger, then the conjugate base is weaker, and vice versa. If the conjugate base is stronger, then we know that the acid will be weaker. So in this case, we have a Ka value of 1.74 times 10 to the power of negative 5, and Ka is basically the relative measure of the strongness of the acid. So basically, the higher the Ka value, the stronger the acid. And for a strong acid, the Ka value is very, very high, which indicates that for a strong acid, there's full dissociation to form its ions. But for a weak acid like CH3COH, is a pretty small Ka value. However, the Ka value of CH3COH is still much larger than that of NH4+. So this is, as you can see, NH4+ is much smaller Ka value. What this means is that the conjugate base of CH3COOH is going to be much it's going to be much weaker, and therefore for the conjugate base of NH4+, which is NH3, so NH3 will be a much stronger base. So basically what we're saying here is that CH3COO minus is going to be a much weaker base. So we say that CH3COOH is a stronger acid, as it has a higher Ka value. Which means that the conjugate base is it's a stronger acid, so the conjugate base is weaker. And if the base is weaker, then only a smaller amount of CH3COO minus will react with water to form OH minus ions. Therefore, there's less OH minus ions formed, and if there's less OH minus, this means the pH will be lower. So a lower amount of CH3COO minus will dissociate to form. Oops, sorry, wrong one. Hence, a lower OH minus concentration indicates that the pH is lower. And this is obviously assuming that the initial concentrations are the same, which indeed they are the same. So you have 0.124 mole per liter of CH3COH. And for the initial titration, it was also 0.124 mole per liter ammonium. So the concentrations are the same. So therefore, since the initial concentrations of the base are the same, we can say that since CH3CO minus is a weaker base, it produces less OH minus ions in water, and less amount of OH minus ions means that the pH will also be lower. So we have a lower pH there. So we want to predict how the pH at the equivalence point will compare to the titration with NH3 by circling one answer. So again, at this point, we'll have to consider at the equivalence point, all of the conjugate base will have reacted to form the acid, and then the acid will further dissociate in water to form some concentration of hydronium ions. So now we're going to be looking at the acids. So in this case, the acid of CH3COH is again stronger than that of NH4+. And stronger means that a higher proportion of CH3COH ions will dissociate in water in order to form, not ions, but CH3COH, a larger proportion of CH3COH will dissociate in water to form CH3CO minus and hydronium ions, H3O+. So therefore, the hydronium ion concentration for CH3COH would be larger, and therefore we would expect again that the equivalence point pH of the sodium ethanoate titration will have a lower pH. So again, it's a lower pH. So we say at equivalence point, all of the So all of the bases reacted to form the conjugate acid. CH3COOH is stronger than than NH4+. So CH3COH is stronger than NH4+, since the pKa value is higher. Not pKa value, what am I saying? Sorry, I'm being very silly today. So the Ka value is higher. So since the Ka value is higher, and Ka is a relative measure of strength of acid, so Ka relative measure. Therefore, a higher proportion of CH3COH will dissociate in water. Forming a higher concentration of hydronium ions. Hence, the pH will be lower at equivalence point for the CH3COO and a titration. And therefore, that's all we really need to say for this question. Okay, so that's it for this paper. And apologies for some of the mistakes I made in the paper. No, it's not some of the pretty silly mistakes there. If you see anything else, please point it out in the comments below. But other than that, I do hope that you enjoyed watching the video, and I hope to see you all in the next one.